Okay, rather than me giving you a word for word definition of osmotic pressure, I want to give you a conceptual definition or understanding, okay? A conceptual definition. So, osmotic pressure is this thing you might have heard about when you were in biology called osmosis. And for osmosis to occur, you have to have something called a semi-permeable membrane. Now, let me help you understand the difference between permeable and semi-permeable. My shirt is a permeable membrane. Almost any kind of liquid will flow through. All right? Make sense? My mouse pad has a plastic surface. Okay? It's considered to be impermeable. Nothing flows through it. A semi-permeable membrane allows some things to flow through and not others. It's paper. I'm not sure that it is. I think paper is actually permeable. Okay? But it might be semi-permeable in certain surfaces. I don't know. Okay? All right. But now, your cell walls, for all those blood cells and skin cells, those are semi-permeable. Okay? All right. So how does that work? Well, a semi-permeable membrane allows some things to flow through and not others. Let's say that on this side of this this is my membrane. Okay? I'm kind of like, here's the membrane. I'm going to turn it up like this, and you're only seeing the edge. Okay? On this side, we're going to have table salt in water. Okay? And we're going to have the same thing on the other side. We're going to have table salt in water. Okay? But in this illustration, we're going to say that this side is concentrated and this is let's say it's just low concentration. That's not matching up very well, but that's okay. Okay, low concentration and concentrated. Okay? Now our membrane, we're going to allow water to flow through. Water will flow through either way, but the salt doesn't. That's what makes it semi-permeable. Okay? Huh? Yeah, it's something like a filter. But see, a filter just keeps out large particles. Okay? In the case of... Huh? Well, that's true. But I mean large in terms of chemistry. Okay? The difference between a membrane, a semi-permeable membrane, and a filter is these particles may be the same size. The water particles and the ion particles may be the same size, but the nature of the membrane keeps one from flowing through while the other does. Okay, maybe it allows only uncharged particles to flow through and doesn't allow charged particles to flow through. Okay, all right. You ever heard the phrase "nature abhors a vacuum"?
What does
okay.
abhors mean?
Doesn't like it. Okay, now it's a common phrase, but I thought maybe you might have heard it. Okay, nature prefers. Let's put it this way. This is something you should remember. Nature prefers an equilibrium. Nature prefers an equilibrium. And we've talked about equilibriums already. That's when things want to be balanced. Okay. Nature doesn't like, and I'm sort of putting people feelings on nature, and nature doesn't have feelings, but we're using it as an illustration here. Nature doesn't like this difference in concentration. That's a disequilibrium. It doesn't like it. Nature wants it to be equalized, in equilibrium. Okay? So if this side is concentrated and this is low concentration, and the water is the only thing that can flow through, what could nature do to get the concentrations to be the same.
Add more concentration.
Okay, but we don't do that. We got a fixed amount of solution here. What are we going to do here that just change what?
Solute.
Not the solute, because the solute is salt. It can't change. It's got to stay the same. It can't flow through. Only water can flow through. But we can change the solvent. The water can flow through over here and dilute the salt. Does that make sense? Well, that's what nature does. Okay? And the pressure of those particles pushing through, remember, pressure is a force acting on an area. And we said when we're doing gas laws, pressure of air is all those particles constantly hitting some surface. Well, the water particles, as they cross that membrane, are exerting a pressure against the membrane. Okay? That's osmotic pressure. Okay? That is osmotic pressure. So the nature wants them to be balanced out, wants the two concentrations to be the same, and in order for that to happen, water's going to flow through in this direction to try and get this to dilute, so you have the same concentration. So by flowing water across, this side becomes higher in concentration, this side becomes lower in concentration until they balance out. Does that make sense? Well, let's say you got 2 glasses of water. Okay? And we got salt water here of high concentration, salt water here of low concentration. You want to get them to be the same. What are you going to do? Mix them together, aren't you? Mix them back and forth until you got 2 cups of the same concentration. Right? That's what nature's doing up here.
So what's the definition of
Osmotic pressure. Osmotic pressure is the pressure of the particles exerted against the membrane,
the pressure of the particles
exerted against the semi-permeable membrane, as they cross from one side to the other. As they cross from one side to the other. Okay? So in our illustration up here, since this side has more salt and this side has less, water wants to equalize it, so water molecules flow through to try and get them equal. Okay? Well, how is that important? Well, let's see. Where, down here? How many of you ever been in the hospital, had an IV in your arm? Okay. Any idea what's in that IV?
salt.
There is salt in there. There's saline solution and whatever drugs they want you to have. Okay? Why do they have to have salt in the solution?
Officer, treatment.
What, Dev? Exactly. Exactly. Let's look at our illustration here. Suppose this is your cell walls for your blood cells called corpuscles. They're not. I don't think they're truly cells because they don't have what a nucleus or something. Okay, I'm not a biology teacher, but that's what I remember that.
Our cells have nucleus.
Huh?
All of our cells have nucleus.
Right. And so the blood things are corpuscles and not truly cells.
But we don't have cell membrane.
What now?
Cell walls. We don't have cell walls.
They do have cell walls.
Come on, humans ain't got no cell walls.
You have all kinds of cell walls.
I mean, animal cells don't have cell walls. Yeah. Well, one of them do.
One of them don't have
Somebody
cell
doesn't
membrane.
have a wall.
No.
Somebody doesn't.
Close that. No, they all got close that. I'm just
All cells have walls.
They don't. No, they don't. Ask Miss Sandler. One of them ain't got them. I don't think humans ain't got a cell wall.
Get him, Mr. Taylor. Get him.
Humans
Okay,
aren't allowed to
listen.
have
Make him
cell
feel
walls.
stupid.
Look, there are differences between plant and animal cells, but cells have nuclei and walls. All of them do. Okay?
Let's put some money
Now, unless I've completely forgotten everything about biology, and I just took a class, a 2-week class in what was the name of that thing? Biotechnology and I forget the other part of it. It's biotechnology and something over the summer. So I'm pretty sure that cells have walls. Okay. Now they may not have something else. Okay. They have membranes without walls or what?
They have cell membranes, but they don't have.
Okay. All right. I see what you're saying. Okay.
Good job, brother.
All right. So membranes instead of walls. I got you. So they have something that holds it together anyway. Right. Okay. So I stand corrected on the term wall. All right.
You're stupid.
Okay.
So what's the definition of freezing point depression?
I haven't gotten there yet. I'm still discussing this. Okay, so let's talk about this a minute. Okay. So if you go to the hospital and they put pure water in an IV, they're going to dilute the salt that's in your plasma. Okay? If they dilute the salt that's in your plasma, then the water that's inside your blood corpuscles are going to leave through this semi-permeable membrane, okay, to try to get the concentration of the salt inside and outside to be the same. And the corpuscles dry up and die. Okay? On the other hand, if your IV has too much salt in it, got more salt on the outside than the inside. No, that's backwards, wouldn't it? Okay, yeah. If there's less salt on the outside, it's going to try to put more water inside to dilute it so they explode. Okay? When you have more salt on the outside, the water flows out then to try to even out and it shrivels up and dies.
Yeah.
Testing. Everybody has about the same. Okay, they know. I mean, it's not like you have more than some Josh or something. Okay, everybody has about the same concentration of ions. What? I can't hear you. Yeah, I'm not sure. It seems to me the effects of dehydration are more a pH change than they are an ion change. But you have to replace ions because when you sweat, your sweat tastes salty. So you're giving away ions that your body needs to have the right concentration. So you have to replace those. That's why you drink Gatorade. Okay?
Gatorade ain't good for you.
Hey, the tank. If you don't.
No, it's not.
Yeah,
It's
it's
not active. It's not good.
Okay, let's not get into the argument what Gatorade's good for, okay?
It's not an argument. That's prime.
I understand.
We're covering the
It's I'm not an expert in this, but it's my understanding that Gatorade's not so good for you during an athletic event, but it's good for you afterward when you're trying to replenish your ions. Okay? All right. Okay, so that's just a biological connection to this idea of semi-permeable membrane. Semi-permeable membranes are selective Semipermeable membranes are selective based on chemical properties. Semipermeable membranes are selective based not on size. That's what you were talking about filtering a while ago. Semipermeable membranes are not selective based on size of the particles. They're selective based on chemistry. Okay? So it's the chemical properties of the things that cross the membrane that the semipermeable membrane separates with, not the size of the particles. Filters separate by size. Semipermeable membranes separate by chemistry. Does that make sense? Everybody got that? So semipermeable membranes separate by chemistry or chemical properties. Not particle size. Okay?